Okay. This is a repeat of a nicer version of the same plot that you saw Monday from Bill Faulkner when he was talking about the state of the experimental art in frequency stabilizing lasers to reference cavities. This is unpublished work out of a lab in Germany in which two small reference cavities were stabilized in vacuum systems, cryogenically controlled temperature. Two independent laser beams were stabilized to these two cavities, and as a test to see how stable they were beat against each other, and the frequency variation, the phase variation in the combined beams was measured, and there's this remarkable result of this purple line less than 30 hertz per root hertz in most of the signal band of interest, LISA. There was some question Monday about what an error point is. What does that plot mean? And I'll try to sketch that on the board just in general. That is, let's say we've got something that combines a couple of beams, and again, out of a set of electronics comes the phase difference between the two beams. And again, there's a control system going to a laser. Now, whenever you have a control system like this, the point is that there's something with gain here that's going to drive the input to zero. And this input is called the error point. And the output is called the correction signal. And the thing called stabilized is neither of these. The correction signal is the inherent fluctuation in the laser before stabilization. The error point can be anything. If it's too big, you just turn up the gain of this amplifier. And it's a misconception, and I think the misconception may even have persisted in the publication of this experiment, that it's impossible to suppress the error point below shot noise. That's not true. If this level here is just at the shot noise level of the light coming in, you increase the gain a factor of 10, and it's going to go, that voltage will go down a factor of 10. What it means is you've imposed the shot noise somewhere else in the experiment, but it's simply a matter of electronics what that error point is. It's nice to have enough gain to bring you down to the shot noise, but that's not a fundamental limit. So that's why this curve is so small. It doesn't really contain much information. This line, the stabilized line, is a result of repeating this stabilization setup and measuring the interference between the two beams, seeing what the phase difference is between these two. That's a true measure, to the extent that these are independent, a true measure of how well each of them is stabilized. Okay, so we talked about the transponder concept for dealing with the beams between spacecraft. A new concept, due in most part to Massimo and John, who are here in the audience, is a transponder-free arrangement in which the lasers each laser in each spacecraft operates independently. A series of measurements are made on the phase differences, and that these various measurements are combined to extract the gravity wave signal and remove the noise. As I said, I won't talk about that except to delve a bit into a detail of how that phase measurement can be done in perhaps in a method that's insensitive to the this local electronic oscillator. And this is it's a variation. It's really the offset-free locking concept that we saw before in the transponder concept, but here it's not transponding. It's just measuring. So to walk through it, what we want to measure is the phase difference between an incoming beam and the local laser. As usual, the beams are combined on a beam splitter. They're mixed in a photodetector. There is now an oscillator that shifts the frequency. Now this is the open loop case, so if these were the same frequency, the frequency of the signal coming out of the mixer is now equal to the local oscillator frequency. Typically, this will be adjusted to be higher than any expected frequency difference. So if, for example, you knew that the Doppler shifts would all be less than 5 megahertz, you might make this oscillator 10 megahertz, so that the output of the mixer is always between 5 and 10 megahertz. This box called the phase meter, we'll look into the details in a minute, measures the phase difference between that electronic oscillator and the combination of the oscillator and the input light, and that's one of the signals that comes out of the constellation of spacecraft. And the same trick of making that measurement insensitive to this oscillator is used again here by applying the signal to an acousto-optic modulator, so it's common. Maybe a good homework problem would be to analyze this in a little more detail, with the goal of demonstrating that that the output beam is insensitive to noise on the oscillator. Sure.
So, yeah, the primary method, which is you have the oscillator. Right now, we're thinking about the ultra-stable oscillator.
Right.
And that gives you the standard measurement, 5
That's right.
But then this
acousto-optic modulator. This will impose the frequency shift of the oscillator on this beam.
And that beam interferes with what?
It doesn't interfere at all.
That's sent it back.
Sent back. That's the beam sent back. So it's not really a transponder in the sense that this oscillator is not. This laser doesn't get any signal based on the incoming beam. It just gets a signal from this oscillator.
And so whatever comes out of it is again a carrier, or is a carrier plus?
No, this is very simple. If the laser is oscillating at 3 times 10 to the 14 hertz, and this is 1 megahertz, out here is 3 10 to the 14 hertz plus a megahertz.
So there will be also the fluctuations coming from that oscillator, right?
Exactly. That's considered desirable, though, because it's the same fluctuations. They're the same fluctuations that would be measured in this phase, and therefore, when you process the signals, you're insensitive to that fluctuation. I think you might think of it as conceptually equivalent to the sideband idea, but without the need for imposing sidebands.
You actually written down the equation, you consider the fluctuation from the use of ham?
No, that's precisely the exercise for the student.
So can you write this exercise as I can?
I'll try. It might turn out that when we look at it in detail, it fails.
Well, that's the existing problem for the students.
Okay. I've been told that you've seen the theorem that a linear filter, or you've seen how to deal with a linear filter of a power spectrum. That is, filtering a signal multiplies the power spectrum by the filter squared. So that means I can go through this pretty quickly, or maybe even just skip it. Yeah, I'll just go to the bottom line. That if we use a technique of dealing with laser frequency noise by time shifting, as seems likely now, that the precision with which that time shift is needed is determined by this equation. That is, if the laser frequency noise has an inherent equivalent strain noise power spectrum of this quantity, Hy of f, that the noise after the time shifting and subtracting is done is going to be that multiplied by this small quantity 2 pi f t naught.
To understand what your H's mean?
This is the h tilde y of f is this 10 to the minus 15 per root hertz quantity we had before. It's the uncompensated strain noise due to laser frequency fluctuations. So what I'm talking about is the effectiveness of compensation by time shifting and subtracting. And it's probably not good to cover this at an intermediate level of detail since John's going to get to it. In fact, maybe the best thing is just to move on. Is that fair, John? You're going to talk about the precision required on the time shifting. Okay. Another little technical tidbit that's of some interest is we've talked about a box called a phase meter that measures the phase. What does that mean? How does it work? What's sort of a simple implementation of it? How many in this room have actually used an oscilloscope? Excellent. Okay. So
it was about 40 years ago.
You know what? That's fine. It hasn't changed at this level. Okay, so let's imagine that we're sitting there on one of the LISA spacecraft, and I'm looking at the interference between the laser on the spacecraft and the laser 5 million kilometers away. I've got the two signals combined on a beam splitter. They're hitting a photodiode. The spacecraft are moving at meters per second, and therefore I see a difference in frequency which shows up on that photodiode as a nice 10 megahertz sine wave. This is now time, and this is 0.1 microsecond.
So this is the current coming out of the photodiode?
That's right.
The electrical current.
Right. That's actually what you'd see. Now, if one of the spacecraft moves a little bit, the interference pattern changes. To something like that. Now, what I've sketched is a motion that's about a tenth of one of these cycles, which corresponds to the motion of a tenth of a wavelength. So we want some way of measuring this kind of change in phase. Well, if it were an oscilloscope, what you would do is have a nice little oscillator running to the other channel. And you would trigger the oscilloscope on this oscillator. So what that means is that both this trace and this trace always start when trigger. When this voltage level reaches there. And as a result, as this phase shifted, you would actually see this sine wave move back and forth. So we want a machine that will do that, and we want to investigate the limitations of the performance of that machine. An oscilloscope, by the way, is not adequately accurate. Here's the simplest way I can think of doing it. You've got let's say that the green signal is from the electronic oscillator, and the red signal is the photocurrent, the interfered photocurrent, and we can measure the phase by looking at the times between the zero crossings of those two signals, the time difference. So it's easy enough. When the first guy crosses zero, you start a clock. This is a high frequency clock, so it's going to tick many cycles between that start time and the stop time, which is when the other signal crosses zero. And we can just say that the phase is then 2 pi times that measured time times the frequency of either of those signals, the 10 megahertz or whatever. Now, there are a number of limitations to that measurement. Perhaps the most serious one is noise on that clock. But even in the absence of noise, for the kinds of implementations we're thinking of, at least, there's something called quantization noise, which is that, remember, what we're doing is counting the cycles of that clock. You make the clock as high in frequency as possible. Maybe it's a gigahertz, but it still has a finite number of cycles, and that means that the measurement is going to be stepwise rather than continuous. That is, your resolution for each of these measurements is always plus or minus 1 clock cycle. So what that means, that resolution is then, or the total time is computed as the number of clock ticks divided by the clock frequency, which means that for n equals 1, you've got this clock quantization of 1 over the clock frequency, and that is, whenever there's digitization noise in this kind of measurement, there's a spectrum of noise that corresponds to that digitization, where Q in general, for anything that's digitized, and Q is the size of the smallest increment of that digitization, and here, in this case, it's the number of cycles of the clock. For an A to D converter, it's the least significant bit of the converter. The spectrum is equal to that divided by this square root of 12 times the rate at which the measurement is made. Is this something people have seen? No. Okay. And then we can plug in the quantities and see what that corresponds to for we can put in realistic numbers for, say, a beat frequency of 10 megahertz and a clock of 1 gigahertz. You can see it's probably, as a homework problem, you might be able to demonstrate that this is small enough, or tell me how fast the clock has to be. But let's delve for a little bit into the mechanics of where this formula comes from. So I've got some quantity that's varying. That doesn't seem to be a problem when we've got megahertz of Doppler shift and microradian type resolution. Okay, so I've got 2 more topics, 2 quickies. One is this business about measuring or knowing the arm length. There are 2 reasons I can think of offhand why it's the length of the LISA arms. One of them, the less stringent one, I think, is when you get this signal, you measure the delta L. To convert it to strain, you need to divide by L. For LIGO, at least in my thinking, it's never been much of a concern to know L very precisely, because the signal-to-noise ratio probably isn't going to be very big, at least for some time. But LISA's different. The signals can be very strong compared to the noise, and it's of interest to know the calibration, that is, to know how strong the signal is. So what that means, I think, is that if you have a signal-to-noise ratio of 10 to the 4th, then you'd like to know the length to 10 to the 4th, just so you don't have an error in your denominator, the L part of delta L over L. That 10 to the 4th, measuring the arm length of 1 part in 10 to the 4th is as I say, not very demanding, because that's still hundreds of thousands of meters. But the more demanding requirement is probably that needed for time delay interferometry, where we think the bottom line is that something like 30 meters is needed. So here, as a conceptual way, there are various techniques that have been proposed for doing this. This one I like because it's been developed for other applications in astronomical space interferometry, a mission called SIM, in which you have two acousto-optic modulators you can switch between. They're different in frequency by a small amount, maybe 1 hertz. And so you're switching, I don't know, some fairly fast rate compared to the signal band, maybe a few tenths of a hertz between these two laser frequencies with this little switch generator here. So that you either, and these frequencies are both propagated through the entire 5 million kilometer distance and back. And because they're a different frequency, there will be a different phase in the return signal that's proportional to that frequency difference. That is, delta phi is simply 2 pi times the number of cycles of phase measured. I'm not sure that's clear. Where the number of cycles of phase is the length divided by the wavelength, where that is it's the number of wavelengths in the travel distance. We subtract the two so that we get down here at the bottom line that for frequency differences on the order of 1 hertz, we can resolve probably on the order of 30 meters of distance. There's the catch, of course, that if you change, this only works for the fractional number of cycles. If you have an integral number of cycles on top of that fractional difference, that's indistinguishable as far as this phase measurement is concerned. And that's what I tried to suggest here by the sawtooth, is that there's an ambiguity range that's determined by the frequency difference.
Can you remind us why do we need to know the arm length of 30 meters?
For the time shifting algorithms that John's going to talk about, an error of 30 meters in shifting two signals before subtracting corresponds to the sensitivity level that we're talking about. Okay, so the last topic is another error, another potential error in LISA, and that's the error due to pointing fluctuations in the spacecraft. Those pointing fluctuations turn into phase variations in the presence of imperfections. So to analyze that effect, we need to think about how Gaussian beams propagate. And what I've sketched here is a beam as it might come out of a laser, and I've substituted the entire telescope by a lens, at least schematically, but it's equivalent to a reflecting telescope that we'd use in principle. And the rule for Gaussian optics propagation is this generalization of the ordinary zero wavelength limit approximation. That is, that 1 over this quantity q is transformed by a lens with focal length f, where q is the generalization of the radius of curvature of the wavefront. That is, it's defined by this quantity here. It's a complex quantity. The real part of 1 over q is 1 of the radius of curvature, and the imaginary part is the inverse of the Rayleigh range, I guess. It's lambda over pi w squared. So it's desirable to make the radius of curvature infinite after the telescope. And the reason for that is that makes the telescope equivalent to a point source. That is, the spacecraft is equivalent to a point source, and therefore, just like a point source, the phase at some distant point is insensitive to any angular degrees of freedom of that source. And the error that we're talking about is the failure to meet that criterion of infinite radius of curvature, or equivalently, there's always going to be some waste in a Gaussian beam, as you've learned. Equivalently, the position of that waste is going to be displaced from the rotation center of the spacecraft. So I've plotted here the radius of curvature as a function of the separation, as the distance from the waste. And right at the waste, it's an infinite radius of curvature. At infinity, it's infinite again. And at the Rayleigh range, it's a minimum. Just so you have a feeling for how the radius changes. But the relevant calculation is the effect of an error in that radius of curvature. And that error can come from, or will come from, a number of things. One might be aberrations in the telescope optics. So if this were the ideal, say, secondary of the mirror, typically there are going to be some kind of low frequency spatial variations that depart from that ideal. These might be, the quality of a mirror is typically characterized by, often characterized by one number, the RMS variation in the surface compared to the ideal surface. But more completely, it'll be characterized by a power spectrum, a spatial power spectrum of those variations. But these are typically on the order of the wavelength divided by 15, something like that. Or another error is if the...
Typically, in LIGO, it works with mirrors that are quite a bit better.
Right, but they're also much smaller, and they're not subjected to the rigors of space. But yeah.
Space. I thought space is the most benign of all environments.
Launch. I should say launch.
Okay, so for the size mirrors you're concerned about, and dealing have to be launched, land over 15 is state of the art.
I suspect better than that can be done. The LIGO mirrors are not much better than this for the very low frequency variations. Maybe we don't really care what's happening out at the edge of the LIGO mirrors that much, right?
Well,
Oh, maybe for the thermal things you do.
well, for light scattering, I think they land over 40, doesn't they?
Okay. Same order of magnitude.
The same
Yeah.
ballpark. I mean, the higher frequency stuff they do better.
So we're actually concerned about, for this error, about the very lowest frequencies. And in particular, if this mirror has a focal length of f, some people are claiming that even with a perfect surface, the most significant error is an error in that, simple error in that focus, epsilon. And that, again, it's believed that this can be done at the order of lambda over 15, but not much better than that.
The least mirrors are capturing telescope, right?
Yeah, probably.
So, I mean, the location and focus can be handled at the back end.
Right. No, there probably will be. It probably will be controlled. There will probably be some control system to keep the mirror focused, the telescope focused properly. And then the question becomes, what's the limitation of that control system?
Oh, right. Is it be
You have to sense the error somehow. You know, it's a sensor. Okay. So the claim is, and I actually won't try to step through the algebra here live, is that those errors for the kind of typical, I think I used lambda by 10. Those errors will give an uncertainty in the placement in the position of the waist by in the order of 5 kilometers. And maybe this is a good homework assignment, is to derive that formula. It's not already there. So what that means is that as the spacecraft is rotating, well, if the waist were here, as indicated by this light gray line, you can see a just barely visible gray surface here, that there wouldn't be any phase sensitivity to that rotation. It's like a point source. But in fact, it's rotating about here, and the waist is out here, and that rotation has the blue line, and the phase error is now the difference between the blue curve and the gray curve. And that error, I called it epsilon here, and I guess I called it x down here, is this distance times the cosine of that pointing. Now, typically the angle's very small, of course, so we can use a small angle approximation. And we can convert that into a statement about the spectra so that this, in terms of displacement noise, the spectrum due to pointing fluctuations with the spectrum theta tilde of f is x tilde of f times the error in the waist position times the nominal error from perfect pointing. So this contains, as often happens in these types of error calculations, a product of an absolute pointing requirement and a fluctuation on top of that. If either of these were 0, we wouldn't have a problem, but it's not easy to make either of them 0. Typically, it's easier to drive the fluctuations smaller than the absolute pointing. I guess it's probably in principle you would never know you had better absolute pointing. And so in the error budget, we'll typically allocate more to the absolute pointing than to the fluctuations. And this should be per root hertz again. That is so the requirement is that the product is 200 nanoradians squared per root hertz. You might allocate 20 nanoradians DC and 10 nanoradians per root hertz fluctuation. And that is it.
More questions?
Questions?
John, since you're going to be talking about things that are related to this, you must have some issues you like to raise that would help pave the way.
Well, I was fascinated by the business scheme that Bob outlined, measured the phase difference. But maybe my questions, if they're dumb questions, is best asked offline.
Well, no, that's better in front of the camera.
Well, in that case, it was figure 11.
I don't have numbers on my figures. Page 11.
Just looking at the diagram there, did I understand you correctly that the oscillator, the electronic oscillator, the one that's linked delta up, I guess, that oscillator, any jitter in that oscillator, as it's drawn at least, is reimposed on the return beam?
That's right. That's right. This noise here is modulated on this return beam.
Okay. So, but it's not required to do it that way, right? You could do everything there, but also send the direct return beam F2 back if you wanted to.
We don't need this oscillator. We don't need this connection here. That's right.
Okay.
But I mean, so why bother with it? And the claim is that makes the ultimate measurement insensitive to noise in that oscillator.
Oh, sure, yeah, I was thinking more about but whether it's fundamentally required to have as it's drawn, I'm maybe misunderstanding it, it looks like that oscillator noise, if any, is imposed on the return beam also.
Only on the return beam.
Yeah, but maybe you don't, that's not, you wouldn't be required to do that if you didn't want to, right? You could just transmit it F2 with a beam splitter between that and the acoustic, or the modulator.
We could put a beam splitter here and send it back, right? And that's right. And that way you wouldn't get the oscillator noise on the return beam, but you would have the oscillator noise on the phase measurement.
Okay. Actually, where I was going to put the beam splitter was between the output of the laser and the ECM, just to direct that straight back to the other guy.
Right, and that I think that's equivalent. That is, you still have this presumably undesirable imbalanced case of the phase meter being the only thing that's seeing the oscillator noise.
Okay, I'll have to think about it. I'm actually real encouraged that this kind of diagram is drawn.
Because right now, the way we look at the program, there is the receiving signal actually contains the carrier and the sideband, maybe two something. You mix it with the carrier and the sideband, and then you down convert those two measurements with a local oscillator, and then you take the difference. And so here presumably not only have the carrier count, but you also sidebands that are originate exactly symmetrically.
There are no sidebands on this. It's truly a frequency shifter.
So the claim is you can remove both the USO and USO.
That's the claim. Yes.
It's easy to see.
That's really interesting.
It's not frequency shifted for the return beam, because that's equivalent to AOM. AOM is just beam stuff diffraction.
Right. You know what? I've confused everybody by saying it wrong. Notice the angle of the AOM. Okay, I drew it right, I just didn't say it right. Bonnie's correct. This is the unmodulated beam. The one that goes straight through is unmodulated.
So that does not contain USO.
This one, that's right. This one doesn't contain the USO noise. This one does. It might work the other way, but it's a lot more confusing.
It's in your
Okay, what would help? This is where view graphs fail us. But if I were writing a view graph, I would call this F0. This beam is F0 plus delta F. This is F0.
You did write it that way. You just called it F2.
F2. Oh, I wrote it. Thank you. Okay, so I wrote it right. I just said it wrong.
So I am a little bit lost. But what is the purpose of the local oscillator ultimately?
Okay.
There at all?
The reason, okay, let's forget for the moment about this business with the AOM. The reason for the local oscillator is a couple of things. One is there's a concern that as the Doppler shift goes through zero, this detector might be seeing zero frequency. And so typically we'll set this to 10 megahertz or something like that, so that the signal on the photodiode is never passing through zero frequency.
So the signal on the photodiode is never passing.
Right.
So the beat signal on the photodiode.
The beat signal is always this nice megahertz signal, which photodiode electronics are happy with. Also, it simplifies the phase measurement.
Now, why does it simplify the phase?
Well, I mean, you could imagine doing a DC phase measurement, but how? I mean, you're sensitive to the intensity, so if the intensity gets dim, you don't know the sign of the phase change. So typically for a phase measurement, you have to have some modulation.
Okay. You're beating something at delta F against something at F2 minus F1 plus delta F. So what's going to the phase meter? Is it what frequency?
Well,
It's really just
this delta F gets subtracted, so there's F2 minus F1.
So it really is just so I don't understand why the delta F is helping you in that phase measurement.
Well, the phase meter needs some reference to compare against. So yeah, the fact that it's delta F is
But it never sees the delta. Oh,
the phase meter is always going to compare the phase, just like on the board, between two sinusoids.
yeah,
Okay.
one at F2 and the other at F1 is basically,
That's right.
you know, and delta F,
Well, there's only one sinusoid coming out of here, right?
you know,
And where do we get the other one from? We could imagine installing another photodetector.
oh, I see, okay, okay. I was looking carefully at the diagram. So the other sinusoid is the delta F coming off of that.
That's right.
Okay. Okay, so the,
Okay, so we're out of time. Now that Bonnie has finally straightened me out on this, I can try to get the story right. This is topologically the same as the offset locking technique that we use to eliminate sensitivity to this guy. But now the same frequency noise that's imposed from here through the electronics is also imposed on the frequency shifted beam, and therefore the phase meter doesn't see it. And furthermore, the transponded beam doesn't have any frequency shift. So transponded is the wrong word. The beam sent out by the laser just is the 0th order beam that passes straight through the ALM without any shifting.
okay, and you're going to write an exercise on,
Yeah, correct the mistake on the videotape.
Exercises to do that loop, you'll see why the AOM thermal fluctuations cancel out.
Or maybe to what level they cancel.
Yeah,
That's a good one.
well, okay, thank you, Bob.
Okay.